Hello, this is Mr. Gilmore with the 9.2 Central Angles, Arc Measure, and Length. Today we're going to define a few concepts in the beginning. One concept being what a central angle is, and this next concept is the relationship the central angle has with the arc, measure, and its length. Let's go ahead and dive into our lesson. We start with what a central angle is. So imagine with me, you're given a circle and you have the center of that circle labeled. And then what you do is from that center, you construct two radii. What you have then is an angle constructed on the interior of this circle. However, the vertex of this angle is placed at the center. So whenever we find the vertex of an angle that lies at the center of our circle, we call that then a central angle. So connect that then with the idea of center of the circle, central angle. In our diagram below, we have angle ACB, which is actually defined to be a central angle because C being our center of the circle and the two radii AC and BC form that angle, which then means we have our central angle. Now, this central angle is actually related to an arc. So let's take a look at our diagram below. We're going to use this phrase cuts, okay, or cut. If we take a look at our diagram, we have our same central angle ACB as we saw before. However, notice its endpoints of the two radii. We have this point A and this point B. Notice that then A and B are 2 points on the circle. In other words, A and B form an arc of the circle, arc AB. So what we're going to find then is that this central angle is actually related to this arc. We say that this arc is cut by the central angle ACB. So in our diagram, I would say that the central angle ACB cuts the arc AB. If I were to add in another, let's say another radius here from C, let's make that D. Notice then that I have this angle here, BCD. I could then say that central angle, BCD, cuts the arc BD, right? Because that's the arc being cut by that central angle. Now, as it turns out, there is another significant relationship between that central angle and the arc that it cuts. Remember that all angles have some measure to them. So let's just call this angle alpha, okay? So there's some measure to this angle alpha. Well, as it turns out that this measure of our angle relates, interesting enough, to the measure of our arc. So let me introduce you to our next definition, what we call arc measure. Now, in other words, the measure of an arc equals, yes, that's equals the measure of the central angle that cuts it. So down below in our diagram, again, we know that this angle, central angle ACB, it has some measure to it, right? Remember how we define measure of an angle. It's this amount of rotation that occurs from one side of our angle to rotate to the other side of our angle. And we defined there to be a unit of measure that we apply to that rotation, which is the unit of degrees. So we would say that this angle, central angle ACB, has some sort of angle measure of degrees. Let's call that just x degrees, okay? So it has some measure to it, right? X degrees. Well, what we're saying then with this definition of arc measure is that there is also this same rotation idea from one point on our circle rotating around to the other point of our circle. And because of that rotation, okay, because of that rotation, what we're defining then is that arc to have the same measure of rotation. In other words, the measure of our central angle, ACB, is going to equal the measure of our arc because they're rotating in the same amount of degrees. All right, so that's our first way. We're actually going to see we're going to see another way to measure an arc, but this is our first way of measuring arc by defining the measure of our central angle to then be equal to that measure of the arc that it cuts. So let's do a quick example here with following this definition of arc measure. The definition of arc measure, remember, says that the measure of the central angle is equal to the measure of the arc that it cuts. So in our diagram here with our circle C, and we've got several radii joined in here, which means we've got several central angles cutting arcs. Let's, with some given information, find the missing measures of some arcs that are being cut in this circle. So first of all, what we're given are some missing angle measures. So angle OCP is equal to measure 32 degrees. I'm going to fill that in. And then the measure of angle MCN is 40 degrees. So I'm going to fill that in. Now remember, these are two central angles, and central angles cut those arcs. And the arcs are going to equal the measure of those central angles. Now let's dive into some of the questions below. Let's first find the measure of arc MN. Well, take a look at the measure of arc MN. It's being cut by a central angle, MCN. Because it's being cut by that central angle, by the definition of arc measure, it must have the same measure of that central angle. So the measure of our arc MN is 40 degrees. Let's take a look at the measure of arc OP, our next example here. The measure of arc OP, if you take a look at where OP is, here's OP. OP is being cut by the central angle OCP. And because of that, if we know the measure of the central angle, the arc that it cuts is going to have the equal measure, which means the measure of our arc OP is 32 degrees. Now, let's move on to another arc that we're going to be taking a look at to find the measure of. Take a look at arc NP, this entire arc here, right? All the way from N over to P. But let's take a look at the central angle it's cutting. The central angle that cuts it is the radius from C to N and from C to P. Well, that means we need to know what the measure of NCO is, or we can take a little bit of a shortcut here and find the measure of this arc. We want to find the measure of the central angle that's cutting it, and that will again give us the measure of the arc. But notice that the entire piece of the arc here, the circle from M to P, that's a semicircle. Remember, the one assumption we're allowed to make the entire year is that if angles appear straight, they are, which means MCP is a straight angle, and that being a straight angle means it's a diameter, and diameters cut semicircles. So we know the entire measure of that semicircle is 180 degrees, which then means if we have 40 degrees at MCN, what's left over then for this central angle NCP? It would be 140 degrees because they have to be supplementary. Well, if the NCP is 140, then the entire arc it cuts is also 140 degrees. Now let's do our last example, which we've already actually talked about this one. Take a look at the arc MOP, which is actually this entire semicircle, and semicircles are precisely half of a circle, which means the measure of that would be 180 because it's being cut by a central, being cut by a central angle, which happens to be a straight angle, and all straight angles measure 180 degrees. So see here that with given information about central angles and applying our definition of arc measure, we can actually find the missing measures of our arcs using the information of our given central angle measures. Now, of course, what else comes alongside with some of our new definitions are some theorems that we can add into our chapter 9. Well, this theorem I'm about to talk about here doesn't really have a name. You're going to find it on your postulate theorem handout known as Theorem 9.3. I do want to we're going to walk through this proof here in just a moment, and I also do want to tell you a little bit of a heads up on the worksheet. You're going to be asked to practice this proof on your worksheet, and as it turns out, this theorem has a true converse, which means on your postulate theorem handout, you're going to find that Theorem 9.4 is the converse of Theorem 9.3. Let's take a look at what this theorem states. It says this: if two or more central angles are of equal measure, so imagine then with me, you've got two or more central angles that are of equal measure, then they cut arcs of equal measure. And so down in our diagram below, we see that we have this given circle C with the four radii drawn in, CN, CO, CP, and CQ. And what we're given is that the measure of the central angle NCO is equal to the measure of the central angle PCQ. What we're going to prove is that the measure of the arc NO is going to be equal to the measure of the arc PQ. So we'll prove that those two arcs are of equal measure. Let's take a look at that proof. The proof of this is actually dead simple, and here's why. With the definition of arc measure, we can connect the dots through equality. So since remember, we're given that angle NCO and angle PCQ are of equal measure, well, what do we know then about those arcs? We already know these arcs cut the the central angles already cut the arc NO here, and the central angle PCQ cuts the arc PQ. Well, we know by definition of arc measure that they have to have the same measure. So we'll take a look at step 2. In step 2, I have the measure of NCO is equal to the measure of its arc that it cuts, NO, and I can use the exact same definition to make the exact same statement here in step 2 by saying that angle PCQ, a central angle, is equal to the measure of the arc it cuts, measure of arc PQ. Well, now with a big happy family of transitivity, we can relate then that the measure of angle NCO is equal to the measure of PQ, because right, if the measure of arc NO is equal to the angle NCO, we're given angle NCO is equal to the angle PCQ, and PCQ is equal to measure of PQ, which then, again, a big happy family of transitivity of quality, we've got ourselves the measure of equal arcs. So you're going to see this question appear on your worksheet. Be sure to also recognize that this does have a true converse. I will tell you the converse is dead simple, just like this one. It'll take you no more than 3 steps, as long as you allow yourself to assign statements in the same step that use the same reason. Okay, and if you need to, follow this example. Okay, follow the example of the proof here. Think of converse, right? You switch your given and proof statements. You could actually arrive to the given and proof statement very quickly with the converse of this proof, again, using the definition of arc measure. Now, let's move on to the second way that we can actually measure arcs. So we found that we can measure arcs in terms of the rotation that it occurs by the measure of its central angle. But the other way we can actually measure arc is in terms of its length. What I mean by that is, imagine standing here on point B and you want to walk to point C, but you have to follow the circle path. That means you're walking along the edge of the circle over here to point C. So we're not actually then measuring in terms of the rotation that occurs by the central angle, but rather actually following a linear path, right? Saying that there's a linear distance here that means I can walk from B to C. Now, the text above here is actually doing a little bit of foreshadowing for us in preparation to what we're going to call the fundamental proportion. This fundamental proportion is actually going to relate the measure of the arc to its length. So this few sentences that I want to read to you are going to then tie into this newly created fundamental proportion. So the sentence says, degree measure is a fraction of 360. So think about that. If I were to rotate from the one given ray all the way back around, I've rotated an entire rotation of 360, which means any amount of degree measure of a central angle has then been is really a fraction of the entire rotation of 360. Well, then let's think about what arc length is. Arc length, if you think about walking from point B here to point C in our diagram, what I'm really walking is I'm walking a portion of the circumference of the circle, which means the arc length is actually a fraction of 2r pi. If you recognize that, that is what we saw with our circumference, right? C. So with degree measure being a fraction of 360 and the arc length being a fraction of 2r pi, we actually can form a proportion that relates our measure of the arc to the length of the arc. Now, one other note to make is that you're going to find that there is actually a third variable in here. That third variable we're going to find here in just a moment is the radius, because if we change the length of the radius of a circle, it's going to change then the circumference length of our circle, which means it does change inherently the arc length. Now, in our diagram below, if I were to actually calculate the entire circumference of the circle, all right, the radius of the circle is 12, which means the diameter is 24, which means the circumference of the circle is 24 pi. But with the angle being 90 degrees here, I know that's a fourth of the rotation around, right? A fourth of 360, which means it's going to be a fourth of the entire circumference. That's what I'm stating here in this example, which means it does lead us into our fundamental proportion. Now, before we get to that fundamental proportion, I do want to make a quick distinction in our vocabulary. When I use the term measure from now on, I'll be referring to the degree of the arc, right? There's two different ways we can measure arc. So when I say the measure, that's really short for me saying degree measure. When you hear the word measure, I'm thinking in terms of the central angle, right? That's cutting that arc. Now we're going to juxtapose that word measure against the second way we can actually measure arc, which is in terms of its length. And so this was when if I were to say length, I am referring to this walking distance from one point following the path of the circle to the other point. So we're looking at that linear distance that would actually occur as we walk from one point to the other. So again, the vocabulary we see in the future, when I say measure, you're thinking degree. When I say length, you're thinking of some walking unit distance. Now, let me introduce you to then the proportion. This is the proportion, the fundamental proportion that links the measure of our arc to the length of the arc. Now, the one other thing that was also going to be needed to actually relate the measure to its length is the radius of the circle. So if you notice in the first statement above, actually the first two statements above, we actually have three variables. We have the measure, right, which is going to be represented with M. We have the length, which is going to be represented with this script L. And then we have R, which we've seen R come up previous in our first lesson, where R is simply then the length of the radius. Now, all three of those together go into this fundamental proportion at the bottom here. So make sure you write this down. Now, of course, I will give this to you during the test. However, knowing how to use this is going to be extremely important. Notice that what we find on the left-hand side is the ratio of our central angle, or our measure of our arc, I should say, or the measure of the central angle, ratioed with the entire rotation of our circle, which is 360 degrees, right? Because we said that the measure of an arc is the fraction of 360. Now, on the right-hand side of our equation, we have L, which remember represents the length of the arc, is ratio with this 2r pi. But recognize what 2r pi is. That is the circumference, okay? It's the circumference of the circle. Because the length of an arc is really a portion of the circumference. As it turns out, these two ratios are equal, making them proportional. Thus, we find ourselves this fundamental proportion. So again, make sure you have this written down. We will actually use this in a couple examples that follow the introduction of this fundamental proportion. So let's begin by using our fundamental proportion and finding something missing about our circle. In this first example, I think back to our proportion. There were actually three variables, right? There was the measure of the arc, the length of the arc, and the radius of our circle, which means I need to give you two out of those three so you can actually find the missing third. So let me write that fundamental proportion down one more time. So it's our M, which is our measure of the arc, that's in degrees, is ratioed with 360 degrees, is equal to our script L, which is the length of our arc, ratioed with the circumference of our circle, 2r pi. Now, let's read what we're given. In a circle of radius 12, so there is right here our r value, an arc measures 30 degrees, which means that is our M value. What is its length? Which means the question is, what is L, right? We're going to figure out what the length is. So essentially, we take our values that are given, and let's plug them into our fundamental proportion here. So I'm going to replace M with 30 degrees. I'm going to then have that ratioed with this 360 degrees here. That is going to be equal to this missing variable L, that's what we're looking for, what the length is, ratio with our circumference 2 times 12 times pi. Let's simplify a few things. First, on the left-hand side, I notice that the 30 degrees and 360 degrees, well, the units are going to cancel out, right? No more degrees. But 30 and 360 have a common factor of 30. I can divide 30 out of the numerator and 30 out of the denominator. 30 divided by 30 is 1. 360 divided by 30 is 12. Okay, so now I've got a nice little simple fraction there to work with as I'm going to solve for L. Now on the right hand side, I've got this denominator, which is 2 times 12 times pi. That simplifies then to 24 pi. We are going to leave this in terms of pi, which means I can solve for L very quickly. I just simply multiply both sides by 24 pi. Those 24 pi's cancel out. I'm going to flip my equation around to have L isolated on the left-hand side. What I get is 24 pi, which is really just over 1, times 1/12 turns into 24 pi over 12. However, that can simplify. 24 divided by 12 is 2, and I stick that pi on the very end of it, and there we have it. There is the missing length of our arc in terms of pi. If I were to plug that in to my calculator, I'm going to get something 6 point something in length. And of course, what we have to also keep in mind is that units, what we would use for length, would be units of some sort of linear distance, such as like miles or feet or centimeters. We don't need to apply any of the units. Those units are going to be arbitrary. Because honestly, I could change the units, but it wouldn't change the value that a unit held. It'd still be this 2 pi. So that's an example of where you're given a measure of an arc and the radius of a circle, and you can find then the missing length of the arc. Let's do another example. In this next one, we have a circle of radius 18. That's our R value. An arc length, look at that length, has a length of 12 pi, which means there's our L value. What is its measure? So in this case, we're looking for the missing value of m this time. Our fundamental proportion, one more time, is m over 360 is equal to our arc length L over the circumference to our pi. Let's plug in what we know. We know well, actually, we don't know the measure of the arc this time, but we do know its ratio to this 360. We do know the length of our arc is 12 pi, and we know that our radius is 18. Now, we're going to simplify the right-hand side here. If we notice first, okay, we notice first that I can't really do much on the left-hand side. It's going to remain this m over 360. But I first noticed that there's a pi in the numerator and pi in the denominator, which means those pi's cancel out, which means I'm left with a 12 over 2 times 18 is 36. Take a look. 12 and 36 have a common factor. Their greatest common factor is 12. I could divide 12 out of both of those equally. So I'm going to divide 12 out of both of those equally. So my new proportion I get then, as I'm simplifying the left and right hand side, I get 12/36 turns into 1/3. And take a look, that's going to be a nice little clean fraction for us then to solve for our missing value of m. How we do this? I need to get m isolated, which means I'm going to multiply by 360 degrees on both sides. So note that it's actually carrying that unit with it. So 360 degrees cancels out here, and notice that it's carrying, again, that unit of degree along with it. So I then can simplify our equation. I just have m isolated equals to 1/3 of 360. That's really 360 divided by 3 is 120 degrees, and there is our missing measure of our arc. Okay, so in these situations, I have to give you two of those variables. I either have to give you the radius and the arc length, like in this example, or the radius and the arc measure, like I saw in the last example. In those two situations, you can then find then the missing third piece of our puzzle here, which is either going to be the arc measure or the arc length. To conclude our lesson today, let's just take a look at some statements that involve some sometimes never or always truth to them. So in part A, it's actually part A is going to spill over into part B and part C. You'll see why here in just a moment. So if in part A, if arcs have the same measure, okay, so that means they have the exact same rotational value. That means their central angles that they both have are going to be are equal to each other, right? Equal central angles. Will they have the same length? Well, that is actually going to be a sometime situation. Here's why, okay? If I were to have, let's say, two circles, okay, two circles, here's one, and here is another, okay? And in these two circles, I've got this central angle of x degrees, and in this one, I also have the measure of x degrees, okay? So I know that their measures are the same, okay? The measure of the central angle is the same. Will they have the same length? No, because in one, let's say that I have a radius of 1, and this one I have a radius of 2. That means the length from this arc is actually going to be shorter than the length of this arc because the circumference size is different. However, I could have circles that are of the same radius. So let's say I have these two circles. Again, that their central angles are the same measure. Let's call them x degrees. What if this circle had a radius 1 and the second circle had a radius 1? Their circumference would be then equal. In fact, these two circles would be congruent, which then means, yes, their lengths will be actually the same length. So Will this happen sometimes? Sometimes the case will be true. Yes, this will happen sometimes, either where the radius is equal or the radiuses are not equal. So then let's take a look at how we unpack part B and part C. So the same question applies above. If arcs have the same measure, will they have the same length? Well, then I'm telling you, I'm adding some information for part B. What if you, all right, I'm still asking the same question for part A, but what if the arcs belong to the circles that have the same radius measure? Well, that goes then to our example that we just saw here, where if they have the exact same radius measure, let's call that r, and let's call this one r, and our central angles are of equal measure, right, x degrees, then this would be an always case, okay? Always, 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 if circles have the same radius, then the measure of arcs will, if they're the same, will always have the same length of the arc. Let's take a look and unpack part C. Again, go back to question part A, which is asking this question, if arcs are the same measure, will they have the same length? Well, part C then follows up by saying, well, what if, again, you knew, so I'm asking the same question in part A, but this time, what if you knew that arcs belong to circles that have different radius measures? So what we're saying is, let's say I have this radius of, let's call this, oh, let's say x. And then we have a circle here that, again, has another radius, let's call it y, but we're given that these two radii are not the same. The x is not equal to y. Will the arc lengths be the same, even though they may have, I'll call that alpha degrees, will they have then the same, if they have the same arc measure, will they have the same arc length? And that is a never situation. Never, ever, ever will these circles have the same arc measure if the, sorry, arc lengths if the measures are the same, because these two circles will actually never, ever, ever be congruent to each other, which means their components, even if the central angles are the same, measure will never have arcs of the same length. So this concludes our lesson with 9.2. Be sure to head over to that worksheet and take a look at our relationship of our central angles as they cut those arc measures, and then also we'll take a look at measuring arcs in terms of their length. If you do have any questions on this, on that homework assignment, please do not hesitate to email me. With that, be good and do good.